our procedure. We're going to pull up to an outcrop like this one, and I'm going to tell you which formation it is, all right? And then I want you guys to explore the outcrop and take notes, make sketches, find out what kind of rock types we're dealing with here. Jim, did you just extract some acid? Okay, great. So Jim has some acid. Jim, how many bottles you got? Just one?
I got a box with several.
Okay, so if you want to borrow some acid from Jim, go ahead and do that. All right, you need to give it back to him at the end of the day. But that'll let you know whether or not there's any calcite present in these rocks. All right? So you're going to go and explore the rocks, test them, document them, and then we're going to group up again at the end, and we'll talk about what we found and sort of make sure everyone's seen the same stuff and we can all talk about what it means. So this is stop number 1. You're on Corridor H just before the Baker exit, all right? And the name of this formation is the Tanalaway Formation. All right? I want you guys to figure out what story the Tanalaway Formation is attempting to tell you across this span of hundreds of millions of years. All right? So go up and listen to the Tanalaway. Explore along the outcrop. We'll discuss anything interesting you see. Ready, set, go!
Oof. I just found a good specimen.
Yep, so you got some little calcite veins running through there.
So that, we were just talking.
They're still really calm. How about here?
Thinly laminated.
Yes, still thinly laminated, right? Still really calm. What about right here?
Yeah, it's different.
It's different. How is it different? Get up there, look at it. No.
It looks completely different than that.
Skylar, what do you see there?
It's not as it's not laminated at all, doesn't look like.
Not laminated at all. What primary sedimentary structure do you see there? Okay, quick deposition, sure. And grain size is much larger, right? And that grain size actually is like little chunks of this underlying material. So what do we call that? Where we have a switch from really calm deposition, then it gets more energetic, it rips up chunks of what was already there, and then dumps them again.
Oh man, it's there. I know which one.
Scour your
yeah,
memory
I was
for
gonna
it.
say scour and fill.
Scour and fill, right. A beautiful example of scour and fill right here. So this little horizon right here represents some sort of high energy event, all right? Like a storm. You guys with me? So you're looking here at sort of the geological record of perhaps like an ancient hurricane or something like that.
Cool. Wow.
Yeah, wow. All right. Do you see how radically different this looks from what you saw before? Yeah. And look over here. We're back to these thinly laminated layers here. Although this is a nice big thick layer right here.
Probably doesn't. I think that's what it was.
All right. This is probably dolostone, where if we powdered it, we would get a fizz. But a lot of the
lighter ones.
Yeah. Here, let's just do this. Okay. So if this is the same
This
stuff.
one, right?
Okay.
Scratch it.
There's a little bit.
Yeah, a little weak fizz there. Yeah. So this is a dolostone. Yeah.
That one fizzed.
Fizzed.
It's fizzing.
Good. Nicely done, Skylar. Do you guys see the mud cracks there? What does that tell you?
Okay, which way's up?
Calm, shallow area.
Calm, shallow. So shallow that it was exposed to the air, right? All right. Yeah, calm based on the grain size, and the mud cracks tell you it was exposed to the air.
Is that the thing that was interesting to be seen here?
That's one of the interesting things to be seen here. So,
Salt cast.
to bring you guys up to date, we have found some salt casts, halite casts, which are essentially fossil salt. Does that go along with the mud cracks that we saw earlier?
No. Yes.
Yeah.
Yeah.
It sure does. Because if you are basically in a shallow and arid enough environment to dry the mud out and make it crack, you're also in a shallow and arid enough environment to concentrate the dissolved constituents in the seawater. Dissolve or evaporate away the water, make it more salty. Salt crystallizes on the bottom. Later, the tide comes in or whatever and buries those in mud, and you end up preserving them as salt casts. All right?
Which way is north from here? I'm trying to get like a...
So Skylar, Jim, Skylar's got your salt casts. All right. So you can pass those around, Skylar. I'd love for everyone to see them. Did anyone find anything else interesting around here? I think I found it. How you knew it was a stromatolite?
The like dome-shaped strata.
Can you hear, Mitch?
Dome-shaped strata, you said?
Yeah, it's like dome-like and curved.
And they curve up towards the sunlight. So the stromatolitic layer,
It's heavy.
you see on the dome-like shape. You guys see that? Yeah. Right there. And then there's other ones in here as well. And if you climb up to like right here, here, I'll bring it down to you.
There it is. It's sharp. I just cut myself. Wow.
Oh yeah, that.
Do you see it?
Yeah, and
Yep.
like
So I'm holding
dome-like too.
our first fossil of the day here. All right?
Oh, really?
This is a fossil slime mound. A stromatolite.
Is that what that smells to?
What's that?
That smell?
And a little bit of tilt here could make them upside down, right? To go from this and they're just right side up to this and they're just upside down. But yeah, the doming direction is that way. So that tells us that these strata are older and those strata are younger. So let's just summarize what we've learned here, okay? The Tenalawe Formation is a rock formation that consists of limestone and dolostone, the one that'll fizz if you put acid on it directly, the one that'll fizz only if you crumble it into a powder. And it's very thinly laminated, meaning low depositional energy. In some places, those laminations are broken by mud cracks, which indicate that it got exposed to the air and it dried out. In other cases, the laminations have been ripped up by some scouring high energy event, like a hurricane, all right? And then those little chunks that were ripped up were dumped again. So an example is scour and fill, all right? In other places, we see further evidence of shallow water conditions. That's why you wear the helmets. Shallow water conditions in the evidence from the stromatolites and the salt casts, right? Both of those indicating that the stromatolites have to be within range of the sun. The salt casts basically require very concentrated salty water in order to form, which implies a high rate of evaporation, which implies not very much water depth. So does that all kind of knit together kind of nicely?
Mm-hmm. Yep.
I think so too. So these strata of the Tenalawe Formation are Silurian in age. Silurian, all right? They're around 400 million years old, for a nice round number. All right? Do they represent an episode of rifting, an episode of mountain building, or an episode of not either rifting or mountain building, but just tectonic calm? Tectonic calm. Tectonic calm, because we don't see any clastic sediment here. We don't see any gravel. We don't see any sand. We don't see any mud, right? All of this stuff is just crystallized seawater. So is there any evidence of mountain building here?
Yeah, you can see a mountain.
Yeah, there's a mountain, right? Okay, I love it. Yes, you can see that there's a mountain. Also, so there is evidence of mountain building here, but it's not sedimentological. The sedimentological story here, the story of the sedimentary rocks, is a story of tectonic calm, all right? Of no significant topographic relief, of basically, you know, deposition right at or about sea level, okay? But the evidence of mountain building is the fact that these sedimentary strata are not horizontal, right? They have been significantly tilted. And you guys have passed several areas here where they have been folded. That's what I was looking for down there, is I had a nice example of a fold that was about this big, all right? Think about what it takes to get rocks to fold, right? If you try and pick up one of these rocks today and fold it, you're gonna have a hard time.
Yeah.
You might even cut your hand. So that's evidence of these tectonic pressures applied to these rocks after they originally formed, right? Mm-hmm. So the principle of original horizontality says these sedimentary layers are laid down horizontally And if you find them in a position other than horizontal, that indicates that they had something mess them up after they were originally deposited. It's a very jaunty angle to your helmet there. So there is evidence of mountain building here, but it's structural evidence as opposed to sedimentological evidence. Where are we?
Yes.
We are just before Diamond in the Rough Road. But don't let that throw you. There's no diamonds around here, okay? But Diamond in the Rough Road is just up ahead on the right. So that's our location. This is the Hampshire Formation. This is the Hampshire Formation, like New Hampshire, all right? Go and check it out. Figure out what rock types are here. Documenting these primary sedimentary structures. Look for fossils, and so on.
Found some of those.
Go, go, go.
This is cross-bedding.
Satellites over there still, down there.
I'd be surprised.
Pretty dope. Look at that.
Looks like a little mole.
What is that?
Oh, it looks like charcoal.
Yeah,
Yeah?
yeah. These are little bits of coal. These are little ancient plants.
Like this one?
All right.
Oh.
Little scraps of ancient plants. So that one there is really beautiful because you can see the structure of the branch. You can see that it's got layers, that go around it. You see shale, Arcos, or some kind of
Different rock
sandstone.
types.
Yeah. All right. So like I got a lot of sandstone here behind me. I would probably call this a quartz sandstone, but there's some reddish sandstones that we've seen too. Some of those might be Arcoses. And bituminous coal. So those are the three rock types here: sandstone, red shale, and bituminous coal. All right. What about primary sedimentary structures?
Cross-bedding.
Cross-bedding. Great. What does this cross-bedding tell us?
That it changed
Originally?
No, cross-bedding itself doesn't speak of an orogeny. What does cross-bedding tell us?
water.
There was water, and it was a current specifically. All right. So we have currents of water that are depositing sand and depositing red shale, and in that sand and red shale, actually mainly in the sand, I've seen these little blobs of coal, these little chunks. And in one case, I saw something that looked, for the life of me, I think pretty much identical to a tree branch, kind of cut in half. So it suggests what environment of deposition then? If we've got tree branches and currents of water, and we've got some that are high energy and some that are relatively low energy.
River?
I'm sorry, what? River and the associated floodplains.
Floodplains,
Yeah.
yeah.
So I don't think these are peatlands, Mitch. All right, the coal I know is what took you there. But in order to have a peatland, I'd expect to see big seams of coal, right, that are like a couple feet thick and stretch out as actual stratigraphic horizons. All right. Here we've just got these little chunks, and I think those little chunks correspond to little pieces of plants. So you've got the river channel and then the adjacent floodplain. The main current is in the river channel, so that's where you get the sand. Occasionally it overflows its banks and deposits mud on the floodplain. But in the river channel itself, the mud keeps moving. It doesn't get deposited. So that's why you get these relatively well-sorted sandstones. The formation is called the Hampshire Formation. It's Devonian in age. So remember your geologic time scale: Cambrian, Ordovician, Silurian, Devonian. So we looked at Silurian rocks back there. Now we're in the next period along, the Devonian, and we have a radically different depositional setting, right? So back there, we said we were experiencing tectonic calm, right? Because we didn't see any sand, any mud, any gravel, all right? And now we have a different situation. Does this look like tectonic calm?
No.
No, all right? All this sand that makes this sandstone had to come from somewhere. All the little flakes of clay that make that red shale had to come from somewhere. They had to be broken off of some source rock. So what does this imply has taken place in our region since the Silurian?
Deposition.
What?
Erosion.
Erosion of what?
The first
mountains.
mountain.
And in order to get erosion of mountains, you first need to have
Mountains.
mountains. So what must have taken place?
Orogeny.
An orogeny. All right. So the Hampshire Formation is the sedimentary evidence of this orogeny, this episode of mountain building that happened in the late Devonian. It's called
Truck.
the Acadian orogeny. The Acadian orogeny.
orogeny.
So the Acadian orogeny was caused by a little microcontinent, something about the size maybe of like Madagascar, and it was out there marooned in oceanic crust, and then the oceanic crust was subducted, it smashed into the edge of North America, it shoved mountains up in the air, all right? And you can see the roots of those mountains, the granites and metamorphic rocks at the roots of those mountains if you go to some place like Acadia National Park up in Maine. Here, you don't see the roots of the mountains. You see the lowlands next to the mountains where all the dirt that came off the mountains got dumped, all right? So you're looking at the sedimentary record of the orogeny. This is how orogenies were first defined. It wasn't in terms of the igneous and metamorphic rocks at their roots. It was they were defined in terms of their sedimentary effect on the local area, all right? So all this sand and mud and gravel had to come from somewhere. So yeah, we've got rivers draining these mountains. These rivers are occasionally overflowing their banks. We're far enough along in the history of life that there are plants that are colonizing those sediments. And so we get these little coalified plant remains as well. Isn't this beautiful, this story?
Yeah. It's crazy.
Okay.
The change in color, so there's a lot of green.
Yeah, so there is a lot of green. Great. Betty's made a great observation. So we've got some of these muds that are red, right, indicating they were deposited under high oxygen conditions. And then we've got other muds that have this sort of greenish gray color, all right? That greenish gray color corresponds to what? If red equals high oxygen, relatively low oxygen. So one of the things that often happens in these floodplains is the mud gets deposited, all right, and it's got some organic matter in it, maybe. But then it's buried under a thick enough deposit of mud, which is impermeable, that oxygen can't get down there and oxidize all the stuff at depth. So often deeper down, you'll find relatively low oxygen sediments. So this is something that you may have experienced for yourself if you've ever been digging around in the mud, and at the top it smells fine, then you dig down deep and it starts to stink, all right? That's because there's a totally different community of bacteria living down there in the low oxygen environment. And they're producing hydrogen sulfide, which makes it smell stinky, all right? So probably if you were here 360 million years ago, I mean, there would be no mountains, right? It would be basically a broad, flat floodplain with various rivers snaking across it. And it would all look like sort of reddish soil next to the rivers. There might be some plants growing out of it, maybe along the banks of the river. And if you took a shovel and you dug into it, you might find some stinkier black colored clay, maybe gray colored clay underneath those upper red layers. Okay. The sandstone is the blocky stuff that's got a nice sheen of water on it right now. How many major sandstone units are there here?
It depends. Just two.
Yeah, I mean, I'd say two, roughly. But yeah, you could probably argue with me about that. It depends on what we consider to be significant. How many significant shale units are there here? Two, right? So basically we got shale, sandstone going up the hill. You with me? Mm-hmm. Look at the contact between the bottommost sandstone and the bottommost shale. Look at the contact between the two. The place where the two meet, the lowermost sandstone meeting the lowermost shale. What's the nature of that contact?
Soft sediment deformation.
Soft sediment deformation? That's a possibility, all right? But often with soft sediment deformation, you see sort of a lobe-like shape to of the sandstone, and then little mud flames coming up around the side. And I don't really see that here.
Maybe like a waterway or something like that? Like erosion?
Yeah, erosion. So there's evidence here that there was red shale deposited, and then the high energy water currents that deposit the sand cut into that mud, making little channels. And those channels poke down into the red shale. There are several of them here. 1, 2, 3, a big fat one. 4, another big fat one. 5, another big fat one there. Do you guys see those as we go along? So those may be multiple little channels that are sort of like tributaries that feed into a bigger channel, all right? Or maybe it's like the channel goes into the face of the cliff, comes back out, goes back in, comes back out, goes back in like a tight meander. So imagine like a coiled snake, and then you slice it with a samurai sword and you look at it from the side. You'd see all these little sections of snake, but it's all basically one snake. You with me? So in order to figure out which of those it would be, you'd want to look around at the regional area and see if they match up with examples further away, right? So if they're all like one snaky channel, you'd expect it to be confined maybe in one area. But if it's tributaries, you'd expect them to have a source area where they start, then they get deeper, thicker, in other words, as you go towards the main channel. Yeah, so Kevin asks, is this all still Devonian? Yes, the Hampshire Formation is entirely within the Devonian, all right? The Devonian started way back there in another formation that we didn't stop at, but we'll see the very end of the Devonian further on. All right, I'll point out one other thing here, all right? We gotta get closer to see it, but if you look up there just below the sand, not the little channels that come out of the main body of sand, but at the very top of the mud, do you see some things that look like little vertical stripes, light colored, about the thickness of like a cigar or so?
Yeah.
All right, I'll go point them out. You can key your eye into them, and then I want you to come and join me and look at them.
Oh my god.
I don't see him yet.
My rock goes, okay? Right there. Okay, if you see those vertical things that are about the thickness of a human finger, there's about a dozen of them.
Yeah.
Those are burrows of some organism that burrowed in the mud. And people have suggested that they are lungfish burrows. One of the interesting things that was happening during the Devonian is amphibians were making the transition to come out of the water and onto the land for the first time. So prior to the Devonian, there were no amphibians, there were just fish. And during the Devonian, some of those fish figured out how to do push-ups and walk. And they crawled up out of the ocean, or out of the freshwater, and onto the land, and they tromped around for the first time. They were the first amphibians. Of course, later on, some of those amphibians will go on to become reptiles. They develop a waterproof skin and waterproof eggs, and they were no longer limited to watery regions. And of course, later on, some of those reptiles figured out that they could nurse their young with a nutrient-rich secretion, and they could keep themselves warm by turning their scales into fur instead. And they were the first mammals. And of course, after that, some of those mammals figured out that it was fun to climb around the trees. And they evolved into the first primates. Of course, some of those primates figured out that it was easier to walk around on two legs out in the savannah and make tools and use fire. And those were the first humans. So ultimately here, you might be looking at a trace fossil of your most distant ancestor. So I stopped here to show you a view of something that's pretty cool over across the other way. This isn't as obvious if you're up close to it, if you have it in your face, but if you're on the other side of the road, it becomes a little more obvious. This is one of the two formations that we've already seen. Which one?
The first one. The second one.
Tenalloway I hear, Hampshire I hear. Gosh, how can we tell the two apart?
The Hampshire.
They're strata, specifically what aspect of it? What color was the Tenalloway?
Color. It was more gray.
It was kind of gray and tan, right? What color was the Hampshire?
More red.
Sort of a brick red color, right? What color is this?
Grayish black.
It's got both.
It's a mix of both.
Okay, I would say this looks a lot like the Hampshire. These are these red shales separated by sandstones. They are wet, so maybe that's making them change their color a little bit.
So, yeah, I see the red.
But what I wanted to call your attention to over here across the way is you've got lots of layers of shale, lots of layers of sand. Again, the sand is blocky weathering. The shale makes these little recessed, punky looking surfaces. But right in the middle here, there's a really huge body of sand. Do you guys see that?
Yeah.
Right here about 10 feet up on the other side. It's probably 3 meters thick of sandstone. Trace that out to the left and to the right. What happens to it?
It's so it's like thick and then it gets thinner.
Right. Say it louder, Skylar, so everyone can hear you.
it starts off like in the middle, it's thick, and then it gets thinner out to the edges.
Right, whoops, sorry about that. Yeah, so it starts out thick in the middle, and then it gets thinner out towards the edges. So it's really thick right there. But if you go that way, you see it breaks up into several sand units separated by shales. If you go this way, you see that it breaks up into several sand units separated by shales, and the main sand unit gets thinner and thinner and thinner. That's the sort of package that you would expect for a river channel, right? Which is deeper in the middle and shallower towards the edges, right? So you're looking at a cross section through a river channel there. Not only that, but these river channels often don't stay put. They meander side to side, right? And if you look at it from above, this looks like a wiggly snake. Sometimes it'll pop off these little U-shaped lakes called oxbow lakes. No? Yes?
No.
No.
Cold rain is getting me down. So they're inclined here. I'm going to run over there and I'll point them out. Okay?
We'll come with you.
He's absolutely what?
Oh! Yes. Oh!
I felt that he did it.
Please don't get hit by a car.
You can do it!
Police officer.
Those inclined layers there are the signature of a meandering river channel that started on the left and then meandered towards the right over time. You can see the same thing right here above us. So if you look off to the right here, okay, so you got these flat lying strata down here in the foreground, but up above you've got inclined layers that start on the right, move towards the left, and as they get right here, they make a big smiley face. See that big smiley face with the big sand in the middle?
Yes.
That's the river channel. After having lunch over there. I hope everybody had a refreshing infusion of nutrients.
Yes.
Perhaps caffeine, something warm. We are now back out in the field for our afternoon session, and this is our first stop. What do we call this? Let's call this the end of the Devonian stop.
The end of the Devonian.
End of the Devonian. Okay, Mitch is going to put that helmet on his head in a second. Good. So we are at the end of the Devonian. If you look further down this outcrop here, you see some more of those red beds that characterize the Hampshire Formation. As a reminder, those are red shales alternating with sandstones. All right. Then we get up here, and this sandstone right here, this big sort of tan sandstone, and you can see there's a nice coal seam on top of it, the blackish layer there. That's Mississippian. They call that the Price sandstone, and it's Mississippian in age. So, and remember, the Hampshire is Devonian. So the very end of the Devonian is right here. All right, right here in front of you. This is the boundary between the Devonian and the Mississippian periods of geologic time. What do you see?
Is it disconforming?
A disconformity. Right?
No. What do you see? Look at the outcrop. There's
Oh,
something
folding.
unusual and different here.
Angular.
Folding.
Betty. There's folding. Show me some folding. Betty, you got a helmet on. Go up there. Point out some folding to us.
I said folding too.
Oh, Betty.
Yay, Betty. Oh, yeah.
Oh.
Betty, can you speak up?
All the rocks over here is folded. Right here.
Do you guys see that? How those rock layers there are not planar. They aren't nice little stripes. They're all funky and folded up. And there's like a distinct package of it, right? It's below this big massive sandstone. And it's above this red shale here, this sort of maroon colored shale. And what do you notice about that maroon colored shale? Betty, walk over a little bit to the right. Yeah. Okay, ready? Stop. All right. How thick is the shale right in front of her?
Pretty thick.
Pretty big. Okay, Betty, walk a little further. Okay, stop. How thick is the red shale there?
Thinner.
Thinner. Okay, Betty, keep going.
Barely thick at all.
Okay, stop. How thick is it there?
Not thick at all.
Thick, it's up
Much
higher.
thicker.
Oh, much thicker. Much thicker.
Do you see? It extends all the way up to her left, a big little peak of red colored shale. All right? Those are mega flame structures. Really big flame structures. All right? Well, what's a flame structure? Okay, it's part of soft sediment deformation. When you dump a bunch of sand on a bunch of squishy mud, the sand sags down, making big broad lobes, and the mud squirts up, making flame structures. All right? But usually the flame structures are like this big. These are several meters tall. Okay, if you're talking about the Hampshire Formation, a diamond in the rough road, where there were channels in size, all right, those channels were like jagged, sort of. They were cut down in. So if it's soft sediment deformation, the bottom of the sand will be smooth and bulbous, like a pillow, all right? Like you could flip it over and take a nap on it, all right? And in fact, you'll see that that's the shape of these little sandstone bodies in here that are all folded up. But it looks to me like this whole folded up package was dumped on top of this squishy red mud, and it sank down into it with the mud squirting up around the sort of black shale plus gray sandstone here. All right? So that is evidence of a giant underwater landslide. All right? Where you had layers of sand and mud, sand and mud, sand and mud. All right? And if you look at the inside of these sands, you'll see nice little crossbed sets that are about this big. So they were probably deposited by a river, maybe flowing into a standing body of water like the ocean. All right? So maybe like a delta deposit. But then something caused that delta deposit to destabilize, and it went sliding down into the deep with its layers pre-lithification folding up on themselves. And then they squished down into some red mud and sank into it. Let's go take a look at this and see if you guys agree with me about this outlandish story I'm telling you. Look at this.
I was kind of slipping. I think I was like while I was trying to
Put this fold, excuse me, you are in my video, sir.
Just a big schlumpy lumpy.
Yeah, because
all right, so you've got all this squishy sediment, and it slumps down into the deep and it just rolls up on itself. All right.
Wait, hey, Professor?
Beautiful jelly roll structure here.
Is this the third stop or fourth stop?
I think it's fourth.
Fourth, yeah,
Oh,
fourth.
is this the fourth?
Yeah, okay. And there's
Yeah,
five,
it's
right?
the third formation,
right.
right? So we've seen the Tenala Way, we've seen the Hampshire. Now we're looking at something new.
Okay.
Is this the comp formation?
All right. So you see this one, Betty? Look at this.
No, this is the third one, right? We've already been at the top.
It's totally rolled up on itself like a cinnamon roll.
That was the comp?
Yeah.
Okay? So this is like the ultimate in soft sediment deformation. All right? So this is this giant submarine landslide, flowed down into the deep, got all messed up as it went down into the deep, but it didn't get totally disturbed. The sand grains didn't get ripped apart from the other sand. All right? So it was probably one big, relatively coherent mass that deformed as it slumped down into the depths.
So this is the Mississippian Trunk Formation, right?
No, it's not. That's next. They're these big, sort of lumpy, pillow-shaped blobs. All right? I'm not even really sure what to call them. Yeah, I mean, it's soft sediment deformation, but what do I call this chunk? Maybe ball and pillow? That might, that might be a good term. Ball and pillow. Rock. But yeah, if you look at these things in cross-section, they are extremely, extremely distorted. And then the intervening shale is just like pulp. Right? So, I mean, this stuff
Really?
is in the modern day, it's really, really friable, easily broken up.
Really?
But when it originally was deposited, this was probably very squishy, low strength mud. And the sand deposits were relatively high strength, so they fold up and the mud just squishes in between them.
Yeah, that's really good.
You see there's a great big chunk pointing out? Mm-hmm. All right, and then there's another one back here.
Oh, yeah.
Do you see that? those are way, way bigger than the surrounding sedimentary deposit, right?
Yep.
You guys can't see this very well. These guys can, all right? There's one here, there's one here. And let's see. Here's another one. So we've got some big clasts in here. That's what I've been trying to point out. All right, I'll point them out again. Ready? One, two, all right, and three. Okay. So there's great big pebbles in this mud rock. Let's go look at this rock over here that Robin's standing by. And if you look at this one here, let's see. Hold my coffee.
I'm gonna pick it up. Oh.
Yeah, look at this one. Do you see the big pebbles in there?
Mm-hmm.
So we got great big pebbles in an otherwise fine-grained rock. What does that mean?
It's a metamorphic.
No, it's not metamorphic.
A glacier?
Yes, it could be tillite. Diamictites? Yeah, that's the word you're looking for. Yeah, so there is a diamictite here called the Spectikoff diamictite. Here's like a pebble in this diamictite right here. Okay? Here you can see some of these pebbles. This one's probably a better example where you can see them really standing out. But how do we get a diamictite? Quick rate of accumulation, sure. And what's one of the ways that often happens in cold climates? Glaciers. All right. So this Spectikoff diamictite is a distinctive little rock unit. We just walked through the whole thing there. It's only a few meters thick, but it's thought to represent a short-lived pulse of glaciation that affected the Appalachian Basin during the Devonian, the end of the Devonian. And this was basically unknown until about 10 years ago. And so there's active research going on in this when a guy from the Maryland Geological Survey first described it in a series of papers. His name's Dave Brzezinski. And then since Dave Brzezinski's papers, they've opened up this highway. And so this is actually the best outcrop of it that's anywhere around, which is kind of cool. And it's raining.
Yeah.
Okay, so we've got a poorly sorted sedimentary rock. You should take a look at it. This boulder right here is a great one. Robin says we've got some beautiful drop stones in here, so you should check it out. I'll move away. You can take photographs and look at it, and then we'll move back towards the vehicles and get out of this increasingly cool story to be told at this outcrop. Now we're in the Mississippi and we moved up section. So you can see our last outcrop just down the road there. All right? In between, the rock layers continue to sort of dip towards the west. And we've moved towards the west, and now we're higher up in the section. We're in younger age rocks. These are Mississippian. All right? This Mississippian package of rocks has a funny name. They all kind of have a funny name. This one's called the Maw Chunk, and it's spelled like Mauch Chunk. I have no idea where that name comes from. But anyway, this is the Maw Chunk Formation, and we're at one particular unit within the Maw Chunk. But what do you guys see over here to the right?
It's red.
It's red. Good. Does it look like the sandstone, or like the shale, or like the limestone? Okay, good. Shale. Good. And what do we have over here to the right and up above us here?
It's red.
It's also red. All right, some more shale, and there at the very end of the outcrop, you can see a nice thick sandstone body there, right?
Yeah.
So that's the sort of stuff that we're used to seeing, where we've got rivers and floodplains, yeah?
Yeah.
Okay, and then in between, we've got something else. Go check out that something else. What is this unit here? What's the rock type?
Grey-Wacky?
That's a great question. How can we figure out the answer to the question, does it fizz?
Pouring acid on it.
Pouring acid on it. Who has some acid?
Will it
Often.
fizz?
Please go pour some acid on it.
Does
Wait,
it work in the rain? Will it work with water in it?
Why don't we find out?
Nope. No.
Okay, let's try again then. Try this little piece here that doesn't have a stream running over top of it.
Yeah, it does.
Yeah, it does. So it's got calcite in it, so it's what rock type?
Limestone.
Limestone. Okay, so we got a red shale below, and then we got a limestone above, and this limestone has fossils in it.
whoa.
And these fossils are of marine creatures. So in the example I've got here, right up on my thumb, you can see the beautiful spiral of a snail. All right?
Oh.
And this example right here, I've got some big lumpy brachiopods poking out. See those brachiopods?
Where did you find that? On the ground?
Where did I find it? I found it on the ground because I look at the rocks rather than pointing my iPhone at my instructor. I look at the rocks. All right?
Oh, look at the rocks.
Go look at the rocks.
Go look at the rocks.
Go look at the rocks.
Looking down the outcrop this way. On your immediate left is this red shale and these big, thick channel sandstones. Where most of the students are, they're looking at this package of limestone, which is called the Reynolds limestone. The Reynolds limestone member of the Maw Chunk Formation. So just as an hour can be subdivided into minutes and the minutes can be subdivided into seconds, the Maw Chunk Formation can be subdivided into smaller units that are called members, all right? So this particular package of limestone, which is about 4 meters thick there, that's called the Reynolds limestone. It's a member of the Maw Chunk Formation. Formations can also be grouped together into bigger units called groups. And groups can be grouped together into bigger units called supergroups. So supergroups are the biggest sedimentary package. They're subdivided into groups, which are subdivided into formations, which are subdivided into members. And then within those members, there might be certain beds that you could identify and give names to. Like the stromatolite bed we saw in the Tenalloway Formation. So, so this is the Reynolds limestone member of the Maw Chunk Formation. Given that we have red shale at the bottom, red shale at the top, limestone in the middle, what's the story here? The overall story of this outcrop? So this stuff looks a lot like the Hampshire, right? And we interpreted the Hampshire as these rivers that had these well-oxidized, muddy floodplains associated with them, right? So this looks a lot like that. But the limestone looks nothing like the Hampshire. So when I first came here, I thought this was the Hampshire, all right? And it took me a minute to realize that I was above the Hampshire. But this limestone is weird, right? Relative to those sort of river floodplain environments. What story does the limestone tell? What must have come up? Okay, so all this stuff has been tilted by mountain building, okay? But if we restore it to its original horizontal orientation, we've got a vertical sequence of sediments. Red shale and sandstone, limestone, red shale and sandstone, all right? So in other words, we've got clastic sediments topped by limestone, topped by more clastic sediments. We've got terrestrial deposits topped by limestone, topped by more terrestrial deposits. How can we explain that pattern? So superposition tells us that the oldest is at the bottom and the youngest is at the top. These aren't the same red shale, they're two different red shales.
Okay.
Mitch, what's the story here?
So sea level was back, well, it was lower here. So then, I think it was a Thursday lecture where you start to get the sand pushed further in, the limestone moves in, and then it regresses and goes that way.
Oh, that's right. That's what we're looking at right now.
That's what you're looking at. So for those of you who didn't hear Mitch, what you're looking at is a transgressive, regressive sequence. A story that basically says sea level was lower than these sedimentary deposits, sea level is higher in these sedimentary deposits, sea level is lower in these sedimentary deposits. All right? So we have a story here of sea level rising relative to the land and then falling again relative to the land. So when sea level is lower in the land, you get these red floodplain shales and channel sandstones. When sea level is higher, you get these limestones full of marine fossils, all right? And then sea level drops again, and the river and shale package moves back out over the area again, okay?
Mm-hmm.
So this is what it looks like. I mean, this is the sort of evidence that we look to when we want to say something about what sea level was like during a given period of time. So back at the beginning, our very first stop, the Tenalloway, we were basically at sea level, or pretty close to it, right? And we know this because occasionally it dried out. Mud cracks, salt casts, yeah? All right? And then we get into this period of time when we're above sea level and we've got rivers coming through, flooding periodically, dumping a whole bunch of clastic sediment. Then it appeared to have gotten deeper again when we got that submarine landslide there. And that deepening may have had something to do with glacial loading. right? When glaciers pile up on the land, they push the land down, right? Is this hail?
Yes, it's hurting.
Okay.
No, it's not hail.
No. Poor Matt. You can go cower in the van if you need to. And now we're back into these sort of just above sea level river and shale packages, but we're close. And we know this because sea level rose just a little bit for a little while and dumped this package of limestone here. The Reynolds limestone member of the Maw Chunk Formation. So this represents basically the last gasp of high sea level. So this is Mississippian, all right? If you go to Arizona, like to the Grand Canyon, there's a huge, thick limestone there called the Red Wall limestone. And basically, that's the last limestone in North America, all right? The Mississippian is the last time we have widespread carbonate deposition in North America, all right? And then sea level drops again, and we start building up these more terrestrial deposits on top of this brief little interval of submarine deposition.
What causes sea level to go back down?
Yeah. Okay. So what causes sea level to go up or down? So there's a bunch of different factors, all right? One of those factors is basically how big are your oceanic ridges? If the oceanic ridge, where there's seafloor spreading taking place, is growing at a fast rate, if spreading's happening really quick, you get a big beefy ridge there, all right? It's like the East Pacific Rise today, which is massive, right? If it's happening at a more slow, gradual, petite pace, then you get something that's sort of piddly, like the Mid-Atlantic Ridge, all right? The Mid-Atlantic Ridge doesn't displace as much seawater as the East Pacific Rise does. So the number one control on where sea level is how fast is your seafloor spreading. A second major control is what's your climate. If it's hot, you melt off all the glaciers, all the ice, and all that water goes somewhere, it goes downhill, it gets dumped in the oceans. All right, if it's cold, you take water out of the oceans, you lower sea level, and you build it up into ice caps on the land. All right? Plus, there's a whole bunch of other things. Another thing that can displace water is sediment. So if you have high rates of deposition of sediment, that can displace water. And then there's all the local effects too. Is the crust bobbing down or is it bobbing up? All right? And so you can get local overprints on the global story.
So if sediments are being deposited, would that cause it to rise?
So yeah, so the short version here, thank you for bringing me back full circle on this. The short version here is that we have evidence from here in West Virginia and from Arizona and from dozens of other places that sea level was high globally at this time. Remember I talked about these different major sequences of transgression and regression on the North American continent? And I pointed out there were 6 of them, all right? This is the 4th of those 6, all right? And this is the local record of it right here. Everything Matt says, it comes with this sarcastic, sort of drizzle on top.
I feel that. It's interesting.
Robin.
Which sequence was it?
Okay, wait. So, Absaroka.
Thank you.
Yep. So, yeah, it's Sauk, Tippecanoe, Kaskaskia, Absaroka, Zuni, Tejas. Yeah. So, this is the Absaroka transgression.
Absaroka transgression.
Yeah, Absaroka. It's named for a mountain range in Montana, the Absaroka Mountains. Okie dokie, artichoke. So, so what time is it? Seems a coal here. Check it out. Here's one.
It's a lot of coal.
Beautiful coal seam. You guys see it?
Yeah.
This is remarkable stuff, people. Coal is a sedimentary rock that's made out of compressed ancient plants, all right? All the carbon in this coal
Isn't that cool?
got accumulated through the process of photosynthesis. The same thing this grass does when it's warm outside, all right? Sits out in the sunlight, uses this molecule called chlorophyll to take water from the ground and carbon dioxide from the air and use the sun's energy to stick the two together and make glucose. Then you stick glucoses together, you make cellulose, which is the main thing that makes up plants. All right? And if you die and are buried in a low oxygen environment, your carbon doesn't rot, and it stays there over time. And it can be more and more concentrated over time to make these sedimentary rocks called coal. There's different varieties. There's lignite, bituminous coal, anthracite, all right? But they're all coal, fossil fuels, and they are basically ancient dead plants. We can dig them up and we can set them on fire, just like we can with a plant. We can set this grass on fire if it only weren't so damn wet. All right? We can set a log on fire, all right? And we can set a coal chunk on fire. So there's a giant coal-burning power plant right over this hill called the Mount Storm Generating Station, where they dig up coal seams like these and they set them on fire. And by setting them on fire, they have enough energy to boil some water. By boiling the water, they make steam, and that steam turns the turbine. And turning the turbine allows us to make electricity. All right? So this is a major source of wealth in West Virginia. They are very pro-coal in this state. All right? Because this is where, what's that?
Coal keeps the lights on.
Coal keeps the lights on. I'm sure you'll see billboards that say that, or Friends of Coal, We Love Coal. Yep. The reason that they're so assertive about that is a lot of people don't love coal. And that's because when you set coal on fire, you reverse that ancient photosynthesis. So you take that carbon dioxide and that water and you separate them again. And the water and the carbon dioxide go into the air. And when the water gets too concentrated in the air, what's it do?
Precipitation.
Rains, yeah, it precipitates. When the carbon dioxide gets into the air and it gets concentrated, what happens?
Acid rain.
Yeah, you can get a little bit more acidic rain, which can react with the rocks, but that reaction is pretty slow compared to the rate at which water is taken out of the atmosphere. So, because we've been burning coal and other fossil fuels for the past 150 years or so, we've actually jacked up atmospheric carbon dioxide concentrations by about 40%, all right? So we've gone from a concentration of around 180 parts per million to a concentration nowadays of around 400 parts per million. Sorry, that's 280 to 400. And climbing. Every year it's a little higher than the year before. But let's set that aside right now and just look at the interesting thing that's showing in this outcrop here behind me.
What formation is this?
Oh, great question. Thank you, Matt. This formation, which is located right near Bismarck, West Virginia, is called the Kanawha Formation. And that's K-A-N-W-H-A, Kanawha. Yeah, the Kanawha Formation. The rock types of the Kanawha Formation are sandstone, like you see up there. And do you guys see the little white dots in that sandstone? Those are pebbles. So part of that big sand body there are little conglomerate layers. Do you see that?
So hard to see, I'm sorry.
If you don't see it, I'll find a piece of it and show you. All right? So there's sandstone, conglomerate. There's also siltstone, which is a lot of this stuff here, shale. And then there are these coal seams as well. Yes. Okay, Betty, say your question again louder. Now there's no car.
I said, is the amount of coal that's present in the rock enough to say that this is from a peat?
Yes. And so the difference is, back there at the Hampshire Formation, we saw little tiny branches and scraps. All right? Here you've got these long seams. And there's another one up here that goes up the hill and sort of forks. And it looks like a giant dragon's tongue. So my geologist buddies and I nicknamed this outcrop the dragon's tongue for that reason. Yeah, you'll see these coal seams all throughout here. Well, what do you see if you trace this coal seam up?
It looks like an angular unconformity.
It looks like an angular unconformity. Do you guys see that? The coal seam is truncated by the overlying sand, all right? Now, angular unconformities imply some amount of missing geologic time, right? All right? And I think here that it's actually not all that long. So one of the things that can happen, if you've got rivers, like that big sandstone and conglomerate up there, that speaks of a river channel, all right? If you've got rivers that are eroding into a peatland, they can oversteepen some banks, all right? And then this bank, which has shale and mud and peat layers on it, can slump down into the river, all right, rotating as it goes. And I think that's probably what happened to this one over here, all right? And then the sandstone sort of chewed into that slumped deposit. All right. So in other words, I don't think that that's tectonic tilting there. I think that's just, you know, original, like sort of soft sediment tilting of little blocks. Oh, this rain! Ah! I have to get angry to sort of generate some heat. So you guys step back here. I'll put my back to the outcrop so you can see it and look at me at the same time. Okay. So if you look over there across the way, you'll see there's a coal seam that's at the base of this big unit, and it comes up, and then it sort of splits there. Do you see that?
Yeah.
You know, like sort of two coal seams right over there across the way. Big boulder at the base of the cliff goes straight up from that. There's two coal seams on top of it.
I see it. It's like in between that.
Yeah,
Yeah.
with some mud in between. If you go over this way, you can see they merge. They disappear behind the grass there, and then they come out again. You can see there's one seam.
Yes.
All right? Notice also up there, there's a big sort of smiley face channel full of sand. You see that?
No.
Okay, above the coal seams, above the second berm, there's a big smiley face.
Oh, that right there? Oh, I got it. Yeah.
So there's like a sand that comes down, then it's really thick right there, and then boom, disappears. Then another sand shows up over there, right? So these are separate river channels full of sand and gravel.
Oh.
All right? And yeah, that beautiful sort of double coal there, the dragon's tongue, you know, that probably is like these peat bogs that are sitting on top of hills, all right? This wasn't a perfectly horizontal swamp that later got folded. These things actually drape the topography. So if you go to a place like Shetland today, up north of Scotland, it's so soggy there, it's weather like this all year long. I don't know how they deal with it. And basically the whole landscape is mantled in this squashy, mushy vegetation. And on the few nice days they have there, they cut it out of the cliff, they dry it out, and they burn that. It's not even coal yet. But it's basically just, you know, wood sponge material. And if you burn that slowly, you make a nice smoke, peaty smoke that they use to flavor their whiskey, right? So this is a big deal in that part of the world. Okay, do you guys have any questions about this?
No.
Okay, great. All right, well, let's all right. We're back in the Tenalloway formation, the same formation we saw at stop 1. It's actually a lot warmer right now than it was at that last stop.
I'm still cold.
I mean, I'm still cold too, but I'm not freezing like I was back there. So let's take a brief 2-minute moment to get to know this outcrop. Okay, get up there, check it out.
Look at that. Look at those rocks.
Oh yeah, there's a dead animal.
All right, what are we seeing here?
There's a whole skeletal cage over
It
there.
looks like a lot of mud cracks.
A lot of mud cracks. You're right. That is a lot of mud cracks. And the beautiful thing here is you can see that whole bedding plane with all of its mud
that
cracks.
is mud cracks. All of it. Where'd he go? Oh.
Don't they have something like this at the Natural History Museum?
They might. I've got a chunk of this in the Nova Rock Garden. Maybe that's where you saw it. Maybe. So guys, 400 million years ago, this was a tidal flat, all right? As flat as a freaking pancake. Submerged below high tide, but exposed to the air at low tide. And it dried out every day, at least once. And it created these cracks that basically were perpetuated over the years through these like paint layer thin laminations of calcite mud. Yeah, this was the surface of the earth 400 million years ago. Here, I'll stand on it. All right? And obviously it's been tilted out of its original orientation by a much later episode of mountain building. Okay, any questions?
No.
These rocks aren't experiencing like metamorphism. They're just being moved, like shifted because of a rock.
Right, yeah, so this is a question that's actually come up a couple of times. So Betty's question is, these rocks aren't metamorphosed, they've just been shifted or moved, right? Yeah. All right, you don't get metamorphism guaranteed with mountain building, all right? With mountain building, you get compressional forces, but those can take sedimentary rocks and tilt them or fold them. If you follow this up, you can see how the rock layers kind of curve
I'm sorry,
over
I'm very
at the
cold.
top there. All right. But if you subject them to high temperatures and pressures, that's when the minerals become unstable and they react and they recrystallize and they make new minerals. Okay, that's when you've got a metamorphic rock. These rocks are deformed, but they are not metamorphosed. Okay, cool. Well, I guess we can go ahead and get in the vans and head back.